Okay. Yes. Okay. Just now, last class we discussed interrupts due to timer. So we understood how the timer generates the interrupts by enabling the interrupt in a interrupt enable register. Okay. Because before we continue, we'll discuss simple example. One more example. Okay. So here there is a slight change in the way the ISR is written. Okay. The way the interrupt service routine is written. Slight change, not much of a difference anyway. So you can quickly look into this example. Okay. So write a program. There is assembly language program to generate a square wave of 50 hertz frequency on P1.2. You can take any pin for that matter. This is of course this is similar to what we discussed in the last class, except that it uses the interrupt due to last class also we used the timer 0. Okay, so this was uh, for other program anyway. Okay, yeah. So and the frequency of the crystal connected to the microcontroller is 11.092 megahertz. Okay, fine. Just now, so what is the value to be loaded to the timer case? How do we calculate? This is the frequency. Okay, so frequency is given as 50 hertz. Okay, so divide this by that is the total time period is equal to frequency by 50 hertz. Okay, and time period of half cycle is there is a t off and t on is equal to okay. So we get the value as t by 2. Okay, so for this value we are going to program the microcontroller to generate the delay. Okay, so this is going to be the delay to be generated. It is not going to the calculation. So this program it's already calculated as the value to be loaded to the timer is and we are using timer 0 in mode 1. So the value to be loaded to the timer is okay. So we are using sorry, that is timer 0. Timer 0. Okay, value to be loaded to the timer is value loaded. Okay, is given as loaded to the timer is DC. What is the value, guys? Sorry, DC. Sorry, DC 00H. Okay, so this is the value to be loaded to the timer. Okay, to generate delay of t by 2. So the time period is f by 50 hertz. The frequency is 50 hertz. Okay, fine. Let us look into the program now. Okay, yes, now in fact I have copied the program here so that we can directly discuss in the compiler and we can run the program. Okay, it's just like in the last class. Okay, the program starts with the first address, because whenever the microcontroller is reset, it will start from the first location of 00H of the internal ROM space. So long jump main. Okay, so the way we take a main is because what happens is, guys, there is, if you observe the addresses for the interrupt service routine. Okay, it is like this. Oh, sorry, it is hanging. Just a minute. Okay, so the interrupt service routine ISR. Okay, so for ISR, the addresses are allotted in the internal ROM space. Okay, so to start with, for reset pin, okay, so the address starts from 0000. Okay, so for external interrupt 1, okay, sorry, let me open the this interrupt vector table quickly so that we can continue the discussion. Okay, so for interrupt 0, what is the address, guys? Yes, okay, so for interrupt 0, the address is 0003H. Okay, and for timer 0, the address is 000BH. Okay, and for interrupt 1, the address is 00. Yes, it's very easy to remember. Okay, and for timer 1, is any issue is there? Okay, so for timer 1, okay, just a minute, I need to take okay. Okay, so for timer 1, what is the address, guys? For timer 1, the address is 001BH. Okay, and for serial communication, okay, the address is 00. 023H. Okay. Yes, very easy to remember. Reset is 0. Anyway, default address of the program, the ROM memory, where the program execution starts when the microcontroller is reset. For interrupt 0, 0003. For timer 0, 000B. For interrupt 1, 0013. Similarly, for timer 1, 001BH. And for serial communication, it is 23H. So this is what we have written. Okay, so now what happens is, now let us say for serial communication, we have written the, there is the ISR, interrupt service routine. It's the starting address of the ISR of serial communication is 0023H. Okay, so it may continue. Let us say, for example, it may continue up to, let us say, next location is 0024H. Likewise, this will continue, let us say, maximum of up to, okay, assumption, it may even continue behind this, but assumption is, let us say, it continues up to 0030H, maximum of excluding 0030, that is, we can say 002FH, for example. Okay, so thereby, since ISR occupies this address, okay, and this address is default, which we cannot change. Okay, so what we do is, we do not write the main program starting from this address up to this address. Why? Because if you write a interrupt service routine in your program, these are the default locations used by the ASR. We cannot change this address. So thereby, we usually do not write main program in this address until and unless we do not have any interrupts in the program, or we are not going to enable the interrupt. If you don't enable the interrupt, you can start writing the main program from this address only, no problem. From this address, our main code. Okay, if you are, if you have a plan to include to enable the interrupts in your main program, then you cannot write main program in this address, because it is occupied by the interrupt service routine. Better to start main program from the address, okay, main program from the address 0030H, 0030H, because these locations are used by the interrupt service routine. Okay, and hence, when you write a program, though by default it starts from 00, even if you don't write this line, anyway, to the microcontroller start execution from this line. Okay, so we do not want to write our main program in these locations, that is before 30H, that is, I mean to say, this location. Before this location, I don't want to include my main program. That's why what we do is, we take a jump. Okay, so jump to what location? Jump to somewhere main in the same internal ROM space, which starts from the address 0030H. You can change this also. It need not be 30H, guys. It can be 40H also, no problem. Okay, but better not to write the main program before this address, because in case if there's an ISR written, so it will overlap with our main program. So main program will be overwritten. So the execution of ISR will not be proper. Okay, so with that intention, we do not write the main program in these addresses. Okay, so that's the reason why we take the long jump. Okay, again, yesterday we had a question. Should it be long jump or a small jump? Okay, you can use SJMP also. SJMP works within 128 bytes of location. SJMP works. If you're taking, for example, let us say you're taking this to some other address, let us say 1000H, for example, too long a jump above 128 bytes location. That is, if this range is more than 128 byte, then you must use a LJMP. Then you must use a LJMP. Okay. Usually by default, what happens is, of course, LJMP takes at 3 bytes. For safety, we use LJMP. In case even if you write main program anywhere in the ROM space, there will not be an issue with the execution of main program. With that intention, we use LJMP. Otherwise, you can use SJMP. The range is very, very small. Okay. So now let us say use 0040. You need not use 30H also. You can use 0040. No problem. Okay. Because I think, I hope that that concept is clear. That is why do we use why do we use take a jump? Why don't we start from here only? Earlier we used to do that in earlier programs. That is, in normal programs, we have to start from 0000H. Since we have ISR, we don't start immediately. We start after 30H. Okay, you can take any location for that matter. Okay, yeah. So take a jump. We'll go to the main program, which is written at the address starting from 0040H. In my case, in this program. Okay, fine. Yes. Now in this program, I'm using timer 0. Sorry, I'm using timer 0 in mode 1 operation. Just let me jump to the program. I think this. Oh yeah, this was the code. I'm using timer 0. Okay, and the mode of operation is 1. Okay, So for timer 0 mode 1, what is the value to be loaded to the T-mode register, guys? The value loaded to the T-mode register is 01H. Is correct? So this will select timer 0 in mode 1. Okay. And now what is the initial value is for 50 hertz, just now as I had written, so for 50 hertz, so for 50 hertz generation, so the value was DC00H. Okay, but I want to see the execution, and I want to see the effect of generating the interrupt. If I start with this value, it takes a lot of time for the timer to reach FFH. Okay, so what I do is, instead of for DC0H, I start with another value, FFE0H, with the intention that we can early reach the final value so that we can observe the interrupt generation operation. Okay, so that's why my initial value now is FFE0H, just for the decision, discussion purpose. Otherwise, for 50 hertz, the initial value should be DC00H. Okay, so I've taken the initial value as FF to the upper byte of a timer 0, E0 for the lower byte of a timer. Okay, because what is the next step is, next is I have to enable the interrupt due to timer 0. So last class we have seen how to, what is the value to be loaded to the IE register to enable interrupt due to timer 0. So the value is 82H. So if you load 82, this, if this line is not included in the program, there will not be any interrupt generation in the program. Okay, so if you want to enable the interrupt, you have to load a value to the appropriate value to the interrupt enable register. Okay, is what is the next step after the after this, guys? Start the timer. Okay, for timer 0, TR0, start timer. Okay, yes, once the timer is started, what happens, guys? Timer starts counting the clock pulse. That is, for example, we started with let us say FF E0. So next count will be FF E1. Is this continues until it reaches FF, and the application of next clock pulse, the count becomes 0000. At this point, TF0 will be set to 1. Since we have enabled the interrupt, so this will generate a interrupt. This will generate interrupt. Okay, to the microcontroller. When this generates a, that is when this flag is set to 1, this generates interrupt. And then, sorry. Okay, so there's no question there. Okay, so it generates interrupt. It will automatically has to take a jump to the interrupt service routine. For timer 0, the interrupt service routine is is loaded at the address 000BH. Okay, fine. Yes, let us okay. So we'll look into the program till it completes the execution of ISR. Okay, we have to wait for the microcontroller to complete the execution of ISR. For that, we are using a infinite loop. Yesterday, we used one program to transfer data from port 0 to accumulator and accumulator to port 1. Instead of that, we are using a simple infinite loop, which will be executed till the overflow flag is set to 1. Till the overflow, till the overflow, till the overflow flag is set to 1. Once overflow flag is set to 1, it will generate the interrupt. It will go to the ISR, execute the ISR. When on the execution of RET instruction, it will come back to the main program. Okay, and it will execute this line again till the timer starts with the initial value and goes up to the final value. Okay, so this is a infinite loop for us. Okay, okay. So whenever there is a interrupt generation because of the overflow flow of a flag, it will go to the interrupt service routine. For timer 0, as I said, the ISR is loaded at 000BH. Okay, so what is our intention is, we have to generate a square pulse, okay, on P1.2. Okay, so what I do is we are going to complement P1.2 so that we are going to generate a square pulse. Okay, yes, now observe this. After executing ISR, where does the control goes back? Controls goes back to this line. It will never go back to any of these lines. Okay, it will not go back to here. Okay, but I want to continue the operation of generating the square pulse, for which I need to load the initial value. Correct, I need to load the initial value. So thereby, since these two lines are not available in main program, but they are not executed, because after after executing the ASR, it will never go back to these lines. It will continuously execute this line. What we do is, after complementing, that is when the overflow flag is set to 1, after complementing, okay, will not stop the timer. Instead, we load the initial value to the timer and continue with the operation of timer. That is, continue to clock on the clock pulse, and when RETA instruction is executed, it will come out of the main program. Yes. Yeah. Sorry for the interruption. Okay. So when RETA instruction is executed, it will come out of the main program. It will execute this line infinitely. Again, when the timer overflows, it will go back to the main the ASR interrupt service routine. It executed interrupt service routine. Again, it comes back to this line. Okay. Yes. Quickly, let us look into the execution of this program. Build target. Okay, fine. Yes, next is I'm going to execute step by step. Okay, for step by step execution we can use F11 shortcut. Okay, so for this I use port 1 because I already configured. Actually I was checking this program, so I configured p1.2 and I've selected bit so that I observe only one bit of a port 1, that's p1.2. Okay, so let us observe this timer 0 window. This is very important for us now. Okay, yes, now if you can observe, by default it is showing the this SJMP line because say org00 is not an instruction. What is org, guys? It is a assembler directive. Since it's not an instruction, microcontroller start with the execution of this line. Okay, fine. Let us say I'll execute F11. Okay, so the first instruction to be executed is shown by the double arrow, green color. Okay. Yes. Okay. Fine. Anyway. Okay. So thereby, the microcontroller start with this instruction. It will take a jump to the main program. Guys, could you see the control transfer? Guys, it transferred from LJMP instruction to main instruction, loaded at 48 address. Okay, and it will execute the main program. Yes. Meantime, when this is executed, this line is executed. Observe these values are here. Observe these values, guys. What happened to timer 0? Okay. Observe this. So the timer 0. Sorry, I need to take. Okay. So timer 0. Okay. Uh, I'm continuing the execution. Okay. Okay. Yeah. Okay. Yes. Did you observe that the value loaded to the TH and TL is FF and E0. So I've taken the value as FF E0 so that no, so that I can conclude the program faster. Okay. So start the timer. Once the timer starts, it starts to count the clock pulse, and till then it executes the main program. Till then it executes the main program. Meantime, observe TL0 base. TL0. Okay. So once the timer overflows, okay, so it is FB now FD, FF, and once the timer overflows, okay, TF is set to 1. Okay, it automatically jumps to the ISR, which is loaded at 000B, and now it's going to complement. Yes, right now observe this waveform now. Initially it was logic 1. Okay, what will happen to the waveform? Okay, waveform is reset to 0. Why? Because we are using complement function. It was 1, it became 0. Okay, so now we'll continue this operation. Again, we are going to load the initial value that you can observe in this window. There is a TH0 as well as TL0. Okay, so it will load initial value to the timer. Okay, and after loading the initial value to the timer, on the execution of RETA instruction, it should go back to this line, that is ES short jump here. Why? Because this was executed, the interrupt occurred during the execution of this instruction. Okay, so thereby it should go back to the same line. Actually, next line to next to this, since it's an infinite loop, the controller will automatically goes to this line. It will not go to the next line. Okay, there's a question. Oh, I think there's a chart. Why we have to complement? Why? Because we have to generate a square pulse. Okay, for a square pulse, what happens? That let me explain something like this. Okay, okay. So on P1.2, I have to generate a square pulse. Square pulse. Okay. Yes. Let us initially I take P1.2 as 1. Initially, let us it was 1. Sorry, it has a value of 1. Okay. If I complement, it becomes 0. Again, if I complement, it becomes 1. Okay, if I again complement, it becomes 0. Like this it continues, so that it generates a what is known as square pulse. Our ultimate intention is to generate a square pulse of some delay. Okay, there is of some time period, there is some delay. Okay, so this is the okay, you may ask a question. Instead of using complement function, cannot we use set b? Cannot we use set b and clear? clear. Okay, yes, see, instead of each time setting and clearing, okay, better to use complement. That is, this function is can replace two instruction. Okay, each time you have to see. Moreover, how do we know whether it was please mute your audio, guys. Okay, okay, so somebody is singing. Okay, okay, here we go. So okay, okay. Now, mm, I don't know. Okay, yes, anyway. Now, so instead of because let us say I'm somewhere here. Let us say the P1.2 is in a I state. Okay, it has to be reset to zero. How do I know it is I state? I mean, instead of checking this and then resetting it, simply complement. So complement, if it is 1, it will take the control, it will take the pin to 0. If it is already 0, it will take the pin to 1. Okay, so thereby complement function is better than setting and resetting. Okay, setting and clearing. So this one instruction replaces the two instructions. Okay, I hope the question is answered. Okay, so I hope it's somewhat okay. The question is answered. Okay. Yes. Anyway, now let us continue, guys. Yeah. So thereby, after executing RET instruction, it will go back to this line because it was interrupted during this execution of this line. Okay, and this operation continues. Okay, and we can see that on P1.2 it continues to generate a square pulse. So we can observe the operation in both the this timer window as well as on the logic analyzer window. Okay, so thereby the control will automatically jumps to the ASR. Okay, so it will jump to ASR, it will execute ASR, and the execution of RATA instruction, it will go back to the main program from where it left off to the interrupt service routine. For the execution of interrupt service routine, it continues to execute the main program till the interrupt is generated. Once the interrupt is generated, again it will go to the interrupt service routine, execute the interrupt service routine, again it will go back to the main program. Okay, because in this program what we observe is these ORG instructions are not executed, because first of all org is not an instruction, it is an assembly directive. Okay, so it's the instruction to the microcontroller saying that copy this value to the PC and start executing the instruction loaded in that address. Let's observe this. If you place the mouse pointer at the CPL instruction, the address shown as 000B. Similarly, if you place the mouse on the pointer SJMP, it shows address as 000B. Okay, so because org is not a instruction, it is a assembler directive. Okay, so this instructs the microcontroller to copy this value to the program counter and start executing the instruction from that particular address. Okay, so we can quickly see the frequency of the generated square waveform on P2.2, P1.2, sorry, P1.2. So let us see what is the value, guys. I need to closely look. Let me check the frequency directly. Okay, so frequency should be approximately. Oh, sorry, I didn't set the what you call frequency. I guess it should be 50 hertz. Um, okay, okay. Yes, let me check. I think I have not set the frequency build target. Just a minute. It's set 11.05 into megahertz. Debug. Oh, sorry, because I changed the value. Sorry. Yeah, correct. Okay, I changed this value. Okay, let us change the value to. Let me change the value to DC00H. Let us observe that. Change the value to upper bit is DC, and the lower byte was 00. Okay, 00. Okay, yeah. Now it will generate 50 hertz. Earlier I had changed the value. That's why it was showing some other value. So let us check for DC00. It should generate a frequency of 50 hertz. Debug run. Okay, let me run the program. I'll stop. I'll take a particular waveform. So let us say starting from this edge to this edge, the frequency will be approximately. Oh, sorry. This we have to, yeah, approximately 50 hertz. It is showing. Mm, oh, sorry, I didn't change it to. Okay, sorry. In the ISR, I have not changed. I'm sorry. I changed only in the main program. I didn't change in the ISR. Sorry. So this is the mistake. Okay. So this is DC, and this is 00. Okay. Now this should be okay. Now this should generate a what we call frequency of 50 hertz. Let us quickly look into this, and we can continue with the the interrupt discussion. debug, run. Okay, so this is generating the waveform. I'll stop it, zoom all, take a particular waveform, zoom in. Okay, so the frequency should be little zoom out, from this end to this end. Frequency will be approximately 50 hertz, 49.9. Yeah, it is 50 hertz. Maybe I have not properly placed the cursor. Okay, fine. Okay, yes, now let us continue the discussion, guys. So this was about the interrupt due to timers. So we discussed the program for timer 0. Similarly, we can write the program for timer 1. Okay, what will change this? So here it will change it to timer 1, it will change it to TL1. Okay, and it will change the value here. So for timer 1, it may be 10, for example. So the value will be 10, and this address will change. ISR. What will be the ISR for timer 1, guys? It will be very easy to remember, 1BH. Okay. So for timer 0, 000BH, and for timer 1, the only change is 001BH. Okay, the address for what you call interrupt service routine. And of course, you have to change this one. Okay, that is TR1, and you have to change this to this value to timer 1. Okay, let us not go into that now. So these are the changes for timer 1. Okay, yes, now let us continue the discussion. Okay, yes, next is 8051 has two external interrupts. Okay, so what are the external interrupts? It is interrupt 0 and interrupt 1. They are applied to P3.2 and P3.3. So I think if I have the waveform, I can show it. Sorry, I think it is deleted now. Okay, okay, fine, no problem, no problem. Okay, fine. So the signals are applied to P3.2 and P3.3. Okay, so now okay, so now once the signals are applied to the signals can be applied to P3.2. There is pin number 12 and pin number 13. Okay, there are okay. So 10 minutes left for the session. Okay, so there are two types of what is known as external hardware interrupts. Okay, they are called as level triggered and what is known as edge triggered. Okay, so let us understand these two in detail. Okay, okay, yes, for level triggered and edge triggered. Okay, so for that we can understand using we can understand the concept using this diagrams. It is explained separately for timer 0 and timer 1. Sorry, interrupt 0 and interrupt 1 input, but anyway the operation is same. Okay, for both the external interrupts. Okay, so let us say we are using interrupt 0. The pin is pin number 12, that is 3.2. Okay, okay, yes, now this IT0 and I0 are the bits of a interrupt enable register. Yes, let us quickly rush to the interrupt enable register. Okay, so that okay, yes, not interrupt enable, sorry, tcon register. Yes, we had discussed tcon register during the discussion of timers. Okay, so the upper 4 bits of a tcon registers corresponds to timers. We had discussed that the lower bits of a Tcon register corresponds to interrupts. Okay, what are these bits? These lower 4 bits of a Tcon registers are IE1, IT1, IE0, IT0. Okay, what is the operation of this? We'll discuss now. Okay, so these 4 bits are available in Tcon register. Okay, so the bits are IE1, IT1 for this IE1 and IT1 is for interrupt 1, and IE0 and IT0 is for interrupt 0. Okay, fine. Let us quickly go back to this discussion. Okay, just now this what is this IT0 and IT1? Okay, so just now we saw in the Tcon register. Yes, if these bits will control whether the external interrupt is level triggered or edge triggered. For example, if IT0, let us say we are discussing for interrupt 0. If this IT0 corresponding to interrupt 0, if it is 0, then level triggered is selected, enabled. If IT0 of interrupt 0, if it is set to 1, edge triggered is enabled. Okay, fine. So what is this level triggered? Okay, yes, now if it is level triggered, what happens is the signal has to be low for a minimum period of 4 machine cycles. We'll see that now. Okay, so that it generates a interrupt. Whereas if it is edge triggered, okay, it can be that edge triggered when it is enabled as 1, that is edge triggered. Okay, what does the microcontroller does is that it will set IE0 to 1. For interrupt 0, it will set IE0 to 1, and for interrupt 1, it will set IE1 to 1. Okay, fine. Yes, let us look at the operation in detail. Okay, so in the level triggered interrupt for interrupt 0 and interrupt 1 pin. Okay, so normally the low signal is applied to them. There is a low signal to the interrupt 0 and interrupt 1 so that it can generate a interrupt. Okay, low signal in the sense from going high to low transition. Whenever there is high to low transition on interrupt 0 and interrupt 1 pin, it will generate a interrupt. Okay. So now, so whenever, what happens when the interrupt is applied to the microcontroller has to stop the execution of the regular program, and it has to jump to the ASR, interrupt service routine, for that particular interrupt. Okay. For example, what is the ASR for address for interrupt 0? 0003H, and similarly for interrupt 1 it is 0013H. Okay. So now the low signal at the low level signal at the interrupt pin, either interrupt 0 or interrupt 1, must be removed before the execution of, okay, because there is, whenever there is a low signal on these pins, okay, what happens is microcontroller senses the signal. Okay, for example, interrupt 0, whenever low signal, whenever there's a transition of signal from high to low and interrupt 0, microcontroller will automatically jumps to the address 0003H and execute the ISR. Okay. What is the last instruction of an ISR, guys, in any program? The last instruction of ISR is RETA instruction. Okay. This signal, that is low signal applied to interrupt 0 or interrupt 1, must be set to high before the execution of RETA instruction of a ISR. For example, let us say this is 0003H, which corresponds to interrupt 0. Okay. Let us say if the signal continues to be low even after the execution of RETA instruction, what does the microcontroller thinks is that there is another interrupt on the interrupt 0. Okay. So to avoid that, the external device needs to apply the low signal only for a minimum duration, and the signal should become high before the execution of RETA instruction of that particular ISR. Okay. So that the RETA instruction is executed successfully and it will go back to the main program. Or else what happens is, if the signal continues to be low, the microcontroller continues to execute the ISR, it will never go back to the main program. Okay. So thereby the requirement is that the low signal should be applied only for a minimum duration, and before the execution of RETA instruction of that particular ISR, the signal should go back to high, so that it will not generate one more interrupt. Okay. So that is the meaning of this line. Okay. That is, the signal should be held low only for some duration. After that, it should be set to high, so that it will continue the execution with the main program, execution of the main program. Okay. This process is called as level triggered. Okay. That is, the signal should be low for some cycle, let's say for the question, is there any question? Okay, no problem. Okay. So it should be low for some duration. Okay. And it should be set to high before the execution of RET instruction. This method of interrupting the microcontroller is called as level triggered interrupt, or it is also called as level activated interrupts. Okay, fine. Yes. Now, what is this level triggered interrupt? Okay. Yes, I think I have only 4 minutes left. I'll wind up with the discussion of this switch. Okay. Yes, let us say, for example, I'm using interrupt 1, for example, interrupt 0 or interrupt 1. Okay. Yes, let us say a switch is connected to interrupt 1. Push button switch. Switch means push button switch. Okay. One end of a switch is connected to VCC. Okay. One end of a switch is connected to VCC. The other end of a switch is connected to ground. Okay. So when switch is when switch is in the open condition, that is pushback condition, it connects to VCC. Okay. When VCC, that's when high voltage is applied, high condition is applied to interrupt 1, it will not generate interrupt. Okay. Whereas when the button is pressed, okay, what happens is that the switch is connected to ground. When the switch is connected to ground, what is the voltage applied to interrupt 0? 0 voltage. When this transition from VCC to 0 voltage happens at the interrupt 1 or interrupt 0, this will generate a interrupt to the microcontroller. Okay. And this is considered as interrupt, and this push button switch should be pressed for some duration, so that the microcontroller senses the interrupt. Okay. There is, let us say, if the switch is released immediately, it may not sense any interrupt. Okay. There may not be any interrupt operation. Okay. Yes. Anyway, I have left it with only 2 minutes. I have to wind up this session. So I'll continue with the discussion of this level triggered and edge triggered interrupt in the next class, that is on Monday, 3 to 4. Okay. So that's all for today, guys. Okay. Thanks for joining. Yes. Okay. Thanks for joining. See you on Monday.
Thank you, sir.
Okay. Good day. Bye. Happy weekend.
Thank you, sir.
Yeah.
Thank you, sir.
Bye.